Thank you. Yeah, so if you remember last time, we discussed the solution of the Kakeya problem in finite fields that Dvir gave. And the main idea was to use a vanishing lemma that says that if we have m points in n dimensions, then there exists a low degree polynomial whose zero set passes through all of these points. And the degree of this polynomial was at most the number of points to the 1 over the ambient dimension. And it was independent of how the points are living, where they are living inside the space. So today I'd like to prove another theorem, the joints theorem, using this technique. And then we'll see how even to try to get some slightly more refined estimates on the joints problem, we start getting into trouble if we insist on using such a high degree as the one coming from the vanishing lemma. We need some more powerful method that will allow us to use smaller degrees, and that will be polynomial partitioning, which we'll explain today and in the next lecture. Okay. So the joints problem is the following. And let's begin with a set L of lines that live inside Rn. And the lines are finitely many. So here they are. So we say that the point X in Rn is a joint formed by these lines if the lines in this family through the point span Rn. So here I should see at least n of the lines crossing here at this point X, and n of them should span Rn, should be linearly independent. Okay. So it is very easy inside R2 to create a joint. Any two lines intersecting at the point create a joint there because the directions are linearly independent and therefore they span R2. But in R3 already it is more difficult. So here these are three coplanar lines. They don't span R3 where they meet, so they don't form a joint. They need to be non-coplanar to create a joint. So it feels that in higher dimensions, it should be harder and harder for lines to create joints. And this is the joints problem. It says how many joints can be formed by n lines. Here it is. We are given L lines inside Rn. No information about where they live exactly, about their structure, just their number. It's L of them. How many joints are created by them? I should say that this problem first appeared in computer science, but then Tom Wolfe noticed that there are connections with it, between it and the Kakeya problem. So it is a discrete analog of the Kakeya problem in some sense. So it follows this moral that tubes pointing in different directions should rarely meet, as we said last time. And here lines in general should rarely meet in a way that is span Rn. Okay, so let's think about trivial upper bounds to get the conjecture here. So if you look at any joint, you have n lines meeting there at least. So you in particular have at least two lines meeting here at X, at every joint. And these lines meet there and never meet again. So the joints are at most the pairs of the lines. So the number of joints, J, is at most L choose 2, the number of pairs of the lines, which in order of magnitude is about L squared. And this can even be tied in two dimensions. For example, if your lines, so if your lines are arranged so that everyone intersects all others, which is possible inside R2, then you have as many intersections as the pairs of distinct lines. And those are all joints. Okay, so that is a trivial upper bound, and in R2 it cannot be improved. But we said that in higher dimensions we expect better upper bounds, right? And to search for lower bounds, we can think of an interesting configuration that is a grid configuration inside Rn. So here, let me do the example in R3. We have a k by k by k grid inside R3 of lattice points, let's say. So the lines that form these joints are those in the x, y, and z directions. And let's see how many joints do we have. It's the number of lattice points, which is k to the 3. And how many lines do we have? Okay. So let's think about the lines, first of all, in the x and in the z directions. Okay. So in the front plane here, how many lines do I have? I have k horizontal lines and k vertical lines. So in the front plane, I have about k lines in these two directions, but the plane is repeated k times at the back. So this should be multiplied with k. These are the lines in the x and z directions. And then if I look at the lines in the y direction, how many do I have? I have one through each front point in the front plane, piercing through and covering many joints at the back, creating many joints at the back. So these lines in the y direction are as many as the points at the front. I have one through each, so it's about k squared. So in total, I have about k squared lines, which means that I have the joints are k to the 3, their lines are k squared. So the joints are about the number of lines to the 3 halves. That is a lower bound inside R3. And in general, in Rn, a grid configuration will similarly give that the joints in that grid are about the number of lines to the n over n minus 1. So this is a lower bound in all dimensions. And the correct upper bound lies somewhere between this one and the 2, the L squared that we found above. And it was conjectured for a while that this is actually tied up to multiplication with constants, so that this grid configuration is extremal up to multiplications with a constant. Okay, and that is what was solved using the polynomial method, first by Guth and Katz in 3 dimensions, and then by Kaplan, Serrier, and Schusten, and independently by Kilodran in all dimensions. They proved that any L lines inside Rn can form at most this many joints. And here I'd like to describe the proof by Kilodran because it's very, very clean. Right, so let's begin with the L, a set of L lines in Rn. And let's call J of L the set of joints that they form. The goal is to show that the number of joints is at most constant times the number of lines to this power that comes from a grid. And notice that this power it gets closer and closer to 1 in high dimensions. So it really says that there are very, very few joints in high dimensions. Okay, and the idea is, just like we said, we look at our set of joints and we will find the polynomial of very low degree. So for me, the polynomial is usually red, the zero set is red. Polynomial of very low degree, vanishing at all of the joints. Here will be the zero set of the polynomial. And the degree we will use is the one coming from the vanishing lemma we discussed last time. Right. But let's see whether it would make any sense. So here is a sketch of the proof. It's done in 3 stages. So in the first stage, you notice that if you do find the polynomial that vanishes on your joints, then you have control on the number of joints on one at least of your lines. One of your lines will contain at most the degree of that polynomial joints. So you do have a general picture, lines forming joints here. You don't know how many joints are on every line. You don't know how to control all of them, but on one of the lines, you will be able to control them. There will be at most the degree of the polynomial many joints. Okay. Then the next step is to carefully iterate this to get control for all the joints. So that's what we'll do next. We'll iterate this to show that if we indeed find a polynomial vanishing on our joints, then all the joints can be controlled in total by the degree of that polynomial. So the lower the degree, the better estimates you get. And then in the final step, we'll simply apply this for a polynomial that we understand vanishes on the joints, this one of this degree that comes from the vanishing lemma we discussed. Okay, so that is the sketch. And let's begin. Okay. We want to show that if we do find the polynomial vanishing on our joints, then one of the lines can't contain too many joints. Okay. So the proof, suppose not. Suppose this is not the case. Then all lines contain more than the degree joints. Then, for every line in our family, L contains more than the degree of the polynomial joins. So here is the arbitrary line, and here are the joints it contains. We know that they are more than the degree. That is what we assume here. And remember that the polynomial vanishes at all the joints, and therefore on these ones. So P vanishes here. So we see that we have a polynomial that vanishes along a line more times than its degree, and that should mean that it vanishes along the whole line. We discussed this last time. The polynomial restricted on the line is a polynomial of one variable, so it cannot have more roots than its degree, unless it's 0. So we get that for every line in our family that creates the joints, the line must be in the 0 set. So everything is painted red here. Okay, the red property that vanishing happened at the joints extends to all the lines. And now what we'll do is we'll study every joint and see what it means for that joint. Okay, so let's start with any joint in our set of joints. And I'll draw what I know about it. I know that it is in the 0 set, so I draw it red. Here is the 0 set. I can imagine it passing through this point. Here is ZP. But also the 0 set contains the lines through the point that make it a joint. So you also have these lines here through the point, making it a joint. And something we notice here is that we cannot possibly draw a tangent plane to the surface at this point. So it's as if I have a robot head with 2 antennae. I cannot draw a tangent space to my head at the root of the antenna. It's impossible. So I'll draw this, I'll write this and we'll explain it. No tangent space exists to the 0 set at X, at the joint X. So suppose it did, here it is, then it would be tangent to the 0 set and therefore to all the curves of the 0 set through my point. Now these lines are curves in the 0 set through my point. So the tangent space would have to be tangent to those. So these lines would have to be contained in the tangent space. And at best, together they would span that tangent space and no more. So the fact that these lines span Rn means that they cannot cluster on a tangent space, on a hyperplane. And that's why no tangent space exists there. Okay, and now what does this mean in terms of vanishing of polynomials? It means that the gradient of the polynomial, so the vector of all partial derivatives, at X must be 0, no matter what joint I start with. For every joint X, the gradient must vanish. And the reason is that if it didn't vanish, it would be parallel to the normal. It would be the normal to this surface at this point. The gradient would look like this. and a tangent space would exist. It would be perpendicular to this norm. Since this can't happen, the normal must be 0. So we cannot possibly have a tangent space there. Okay, so let's see what we found out. This, if I write it, oops. If I write it out, means that all the partial derivatives of P vanish everywhere on the set of joints. So we started with a polynomial P that vanishes on our joints, and we got lower degree polynomials vanishing on the joints with the exact same property. So if we have assumed that the original polynomial P is the one of lowest degree possible with this vanishing property, we get a contradiction. Okay, so this is a contradiction assuming, if we had assumed from the start that P is a polynomial, a non-zero polynomial of lowest degree, of minimal degree, vanishing on the joints. Okay, and that's it. You start the proof by picking the polynomial, a polynomial of lowest degree with this vanishing property. You assume that the lines, all of the lines contain more than its degree joints, and turns out they don't. Okay, so that's it. And that's really where we use up the joints property. We used it here in this argument. Then we simply need to iterate this appropriately to get control not only on one line, but on all of the lines. So the thing we aim for is that if we do have a polynomial vanishing on the joints, then we immediately get a bound on the number of joints that depends on the degree. And notice this bound is the number of lines times the bound for the nice line from the previous step. Okay, so what's the idea here? You get your polynomial that vanishes on the joints. And you know that on one of the lines you have control. You have few joints on it, fewer than the degree. So you take that line and the joints in it, and you remove it from the collection. You throw away the joints. So the remaining joints are formed by the remaining lines. So, and the polynomial vanishes there. So you take one with few joints and you throw it away. And you keep doing this iteration until you throw away all of the joints. So here's how we do that. You know that there is one line where you have control from step A. So there exists one line in the family with containing at most the degree of the polynomial joints. What we do is we pick it and take it away. Remove it, the line, and the joints it contains from the picture. So in this first step of the iteration, we have removed very few joints, at most the degree of P joints. Okay. And now we got rid of the joints on that line. We need to count the rest. Those are contained in the rest of the lines, not in that one. So they are joints formed by the rest of the lines. So here we go. The remaining joints are formed by the rest of the lines. So they are in the set of joints formed by L minus this line we excluded in the smaller collection of lines. And these are some of all the joints that we started from. They're just those created by the fewer lines. So the polynomial vanishes here. So the polynomial P vanishes here on the set of joints. As soon as we find the polynomial that vanishes on a set of joints, we know that one of the lines contains few joints. And that's how we continue. So there exists line L2 in this family, in the remaining family, after we exclude x1, with a few joints in it, at most the degree of P joints. What we do is we simply remove it again together with its joints. So remove the line and its joints from the picture. So at the second step, we still have not removed too much. We removed at most the degree of p joints again. And we can keep going this way. We're removing the lines one by one. We get rid of all the joints eventually. So the joints in total, because they are all being removed through all these steps, are at most the joints we removed in the first step, plus the joints we removed in the second step, plus the joints we removed in the final step. Each step came from removing one line, so the steps are as many as the number of lines. And the joints are at most the number of lines, the number of steps, times the joints we removed in every step. And that's how you get control on the number of joints as soon as you find a single polynomial that vanishes on them. Right. And finally, to get the full theorem, we just need to apply this nice lemma, B, for a nice degree polynomial. And that will come from the vanishing lemma that we talked about last time. We know that there exists non-zero polynomial in n variables with degree, so that vanishes on all of our joints, and its degree only depends on the number of joints. So the degree is at most the number of joints to the 1 over the dimension. Vanishing on the joints. So we simply, now that we have found the low degree polynomial that vanishes where we want, we go and plug that in here. This means that the joints are at most the degree of that polynomial times the number of lines. And now I put the joints on the left, the lines on the right. The joints to the n minus 1 over n are at most L. And now I raise everything to the n over n minus 1, and then done. So this is it in 3 steps. And the joints property was only used here. Well, maybe in B a little bit, but not that much actually, no. Only in A. And you see that the better degree you can find for your specific choice of joints of a polynomial that vanishes there, the better estimates you get. So this is the important thing. I'm repeating B here. That was the important step that gave control on the joints using the polynomial method. Something to notice here is that you don't even need to apply this on the whole set of joints. If you are only interested in a subset of the set of joints, then you would run the same argument for that subset, and you would show that the subset has size at most bits. So why am I saying this? Suppose that we wanted slightly more refined estimates. What do I mean by that? Let's say that we want to count the k-rich joints. So joints lying in about k over lines. So let's say I want to control the joints, not only the number, not only how many they are, but also according to how many of my lines pass through each. So that's a point line incidence estimate that actually has connections with the maximal Kakeya conjecture, which we haven't talked about. But anyway, it is interesting for that reason. So let's say that JK, we define it to be the set of joints that lie in about K over lines. So for every joint in JK, I will see about K lines of my family passing through it. So a set of joints such that about K lines in L pass through X. And by about K, let's say we mean at least K and fewer than 2K. So these are the K-rich joints. So what we proved, let's say that we work in R3 for simplicity. In R3, we proved that all the joints are controlled, and therefore the k-rate joints are also controlled by the same upper bound that would come from a grid. This is L to the n over n minus 1 in 3 dimensions. But also a fact, turns out, is that again in R3, the number of k-rate joints is much smaller. It's at most L to the 3 halves over k to the 3 halves. We have not explained this, but actually it holds. The question is, how can you prove such a thing? It's stronger than the above. So let's make an attempt to prove it using the above lemma and combining it with a vanishing lemma, see what we have. So all we need is to find a low degree polynomial that vanishes on our k-rate joints. And then we'll plug that into here and get a bound. So we know that from the vanishing lemma, this parameter counting lemma, that there exists p non-zero in n variables of degree very small, that only depends on the number of our k-rate joints. So with a degree at most, the number of k-rate joints to the 1 over 3, that's the dimension now, vanishing on jk. That we know. So now we just know immediately from the lemma above here that the k-rate joints are at most that degree, jk to the 1/3 times L. And if you rearrange like before, you unfortunately don't get anything better than the upper bound for the joints. So that's no good, even though you use the smaller degree actually than the full set of joints, the 1/3, still didn't get you anything better. So here is where polynomial partitioning comes in. That's a way to motivate it, and that's why I chose partly this problem. There are situations where you would like to know that your points live on lower degree varieties than the one coming from the vanishing lemma. And that is what polynomial partitioning will help us with. So here is this advantage relative to, haven't said what it says, but here is the advantage and the moral we should remember, relative to the parameter counting vanishing lemma. If we start with any finite set of points, S in Rn, the parameter counting lemma would say that yes, we can find a low degree polynomial, degree at most, the number of points to the 1 over n, vanishing at all the points. That's what it says. I want a smaller degree under conditions. I want to be able to use the structure of the set of points to get a lower degree than this one, if I'm lucky. And polynomial partitioning helps with that. So it may allow us, if we're lucky, if the problem works in some sense, to find a polynomial of much smaller than the degree, much smaller than expected, doing what we want, vanishing where we want. And smaller than expected, I mean considerably smaller, hopefully, than the number of points to the 1 over n, which would come from parameter counting, and which doesn't take the structure of the points into account, only their cardinality. So if we're lucky, we will be able to find a polynomial of smaller than the degree than this one. That does what? Well, it doesn't exactly vanish everywhere, not on all the points potentially, but it will vanish in a big proportion of our points. So say more than 50%, or more than 1%, that's still enough. And this property, because this vanishing property will happen on our points, on a big part of our points, and those points will populate our lines, then it will propagate, this vanishing property will propagate to many of our lines as well. Okay, so this is the idea that if we're lucky, polynomial partitioning will allow us to reduce to the case of points and hopefully lines in our family clustering on a low degree variety. A much smaller degree variety than the one coming from parameter counting. I want to say that, you know, losing a proportion of your points and your lines is all right, because the problems we're interested in count incidences in terms of order of magnitude. So if you pick 50%, say, of your k-rich points, and you control the incidences for them, you don't lose anything. You have controlled them all. Okay, so this is the moral, that it reduces to situations where everything clusters, points and lines cluster on low degree varieties, lower than expected. And the question is, why would that be useful? Not merely because of the example I showed you earlier, you know, okay, with the joins, you know, you get at most the degree of the polynomial times the number of lines. Okay, computationally, it is obvious that in this specific example, finding a low degree polynomial helps. It gives better upper bounds. But why does it really help? Why has it revolutionized incidence geometry and even harmonic analysis? Is there a deeper reason than simply computational bounds? Or is it just a magic wand? So this is not really a magic wand. There are reasons why the polynomial method is so effective, and it has to be tailored to a specific kind of problem. So the problem is that when you count incidences, you may encounter pictures of this sort that we saw earlier, all the lines clustering on a two-dimensional plane. Now, this is bad for incidences when you try to control them, because you get so many in this case, as many as possible. Every line can intersect every other inside the plane. So this clustering of lines on this plane is bad. It's a situation we have to deal with, especially perhaps. And the plane is a 1 degree variety. It is the zero set of a polynomial of degree 1 of a linear polynomial. And also, if in general, on low degree varieties, when lines cluster there, we get a lot of incidences. So let's look at a hyperboloid of one shape, for example, that is a doubly ruled surface. And this means that through every point of the hyperboloid, you get two lines through it, fully in the same picture, in the same hyperboloid. So that's what doubly ruled surface means. This means that if you look at this line in your picture, and you're considering points on the hyperboloid along that line, there is always another line that crosses these, still inside the hyperboloid. So you still can get a lot of incidences on low degree varieties when your lines cluster there. And this is true for a saddle as well, for example. So lines clustering on low degree varieties generate many incidences. That's a reality. And every time we have a point line incidence problem, where we try to control incidences of a certain form, we will have to deal with situations like this eventually, because these are bad. These are the bad examples. We want to deal with these bad cases. The polynomial method and polynomial partitioning reduces to such cases. That's what we just said. It allows us, if we're lucky, to reduce the case where everything clusters on a low degree variety. So that's what polynomial partitioning does. It reduces, in some sense, the extremal cases. We don't know they are all the extremal cases, but they are definitely bad, because we can say that. And without us needing to show that they are extremal, the polynomial method gets us there. By passing through all obstacles, it gets us there. If the problem has this kind of property, that these are extremal cases. So it is not a magic wand, it works because of these bad examples, and it reduces immediately to bad examples. So it gives you a nice variety to work with, without you having to show that that's an extremal case. Okay. So let's see what it says. It won't be obvious at all at first glance why it says what I said, that points are clustering on low degree varieties. It won't be clear, but we will see it by and by. So let's begin with any finite set of points, just like for the vanishing lemma. And it's important that we are in Euclidean space. Polynomial partitioning doesn't work anywhere else because it requires topology. And let's take now any degree that we like. So not the number of points to the 1 over n, any degree we want, any quantity that is interesting, that is small, that is at least 1, so that it can play the role of a degree of a polynomial. Then polynomial partitioning, the lemma here says that there exists a non-zero polynomial in n variables of degree at most this quantity, arbitrary quantity you decided you want, of degree at most this d, such that its zero set zp doesn't necessarily pass through all of our points. No, not like in the vanishing lemma. But it splits our points in sort of equal parts. It chops up our set S in sort of equal parts. So the parts we will call cells. We know how many points we have in every cell at most. We have a control here, and we know how many cells we have. Okay, so let's see, let's write this out and understand a bit better. So the zero set will split Rn in a number of parts we can control, in about d to the n parts, and the parts we call cells. D is the degree you fixed at the beginning. So d to the n, the number of parts fully depends on the degree you chose and nothing more. And by cells, as we will see exactly what they are, but they will be connected components like this of Rn minus the zero set. So these the cells will be connected components of this sort. So we know how many parts the picture is split in, and we know how many points we will have at most in every part. So each cell will contain at most its fair share of points, at most the average points, literally average, the number of points over the number of cells, points of S. Okay, so we know how many parts we have, and we know at most how many points we have in each part. This is a number we understand, the upper bound, the number of points inside every cell, because we know how many cells we have, given the degree we chose. This will be the number of points over d to the n, up to a constant. Okay. So this is precise. It really doesn't look like it says what I claimed it said. It doesn't say that your points are clustering on this zero set. No. So what I'll do is today I'll prove this, and next time we'll explain how to use it. But I'd like to explain how you get, like a glimpse of how you get to this point where everything will cluster, pretty much everything will cluster on the zero set in this picture. So the way you deal with problems is you write this out, you chop up the set you're interested in smaller parts, and then you say we have two cases. Case one is the case where what I want doesn't happen. Most of my points live inside the cells, inside these connected components, and not on the zero set. So more than 50% of the points in S live in the cells, and they don't touch the zero set. And case two is the complementary case where more than 50% of the points actually live in the zero set. And that is what I promised, in some sense. I have the majority of my points being in the zero set. So the polynomial in case two will vanish on most of my points. So that's good, that's where I wanted to get, but I still have case one. Okay. a cellular case. And the idea is that case 1, you get rid of it somehow, if you're lucky. Okay? We'll explain how to get rid of it. It's quite standardized. If it works, it's quite standardized how to get rid of it. So eventually you get to case 2. And always behind getting rid of case 1 hides the structure of S somehow. You need to know what kind of points you're looking at to get rid of case 1, because you may get rid of it by using induction. Like we see that we can work on a cell of average behavior, like fewer points, fewer lines, do some induction. Induction means that some specific estimate, you really believe in it, so it must have to do with the structure of the points. So using the structure of your points, you get here where almost everything clusters on a low degree variety. And hopefully the degree you chose here is smaller than, quite smaller than the number of points in the 1 over n, which would be the one coming from the vanishing lemma. Okay. So that is the general idea of why polynomial partitioning reduces to everything clustering on a low degree variety. And we said that this is useful because those are bad examples that at some point or other we have to deal with. So more on that next time. Today we'll just explain this lemma here. Why does there exist a polynomial like this that splits our set in this form? Okay, so we begin with our points here, and what we'll focus on is first, okay, we've picked a degree, it's chosen now, and this means that we know how many cells we want to split. This is prescribed now. Once you fix the degree, you know how many parts you want to split. And the idea is that you bisect your set and you keep bisecting until you get the prescribed number of cells, the one you had decided from the start. And when you do, you stop. And you see that the degree you have accumulated all the way will be at most that big. So, general sketch, and we'll see the details. First, you take your points and you bisect the set at like 2 parts. Like on this part, you have at most half the points, and on this part, you have at most half the points. So you have 2 cells now, with at most half of the points in each, at most the average in each. And now you have 2 sets, and you bisect both at the same time with a polynomial of very low degree. You can do that, we'll see that. And now you have 4 cells, each containing at most its fair share of points. And now you again have 4 sets. You bisect all of them with a 0 set of a low degree polynomial simultaneously. And now you have 8 cells, each containing at most the average number of points, and so on. You stop when the number of cells becomes what you wanted from the beginning. And you notice that the degrees, the 0 sets you partitioned with, you accumulated along the way, together they don't add up to much. They will add up to at most 50. Okay, so it's a bisection method forever until you get where you want it. And let's see the proof, because it's very nice. So here is where topology is used. We use the Borsa-Coulomb theorem, which says that if we start with a function from a sphere into the hyperplane below, okay, that's important, that is continuous and odd. By odd, we mean that antipodal points are mapped to opposite vectors. Then there will exist a point that's mapped to 0. There exists a point on the sphere such that f of x is 0. Okay, and why would this have anything to do with bisection? Well, it will give us a bisection lemma that's very, very analogous to the vanishing lemma. So for the vanishing lemma, you had m points. Here we have m sets of finite and positive volume. So we have volume here. For the vanishing lemma, you would find polynomial of low degree, degree at most, the number of points, the 1 over n, whose zero set passes through all the points. Now, in this version, we can find a polynomial of the same degree, at most the number of sets to the 1 over n, whose zero set bisects, volume-wise, all of these sets. So that's what will happen. And let me write this. It says that there exists polynomial non-zero in n variables. And that's in Euclidean space only, because we will use the Coulomb theorem. Of degree, at most, the number of sets now, m to the 1 over n, so just like the one we're used to, such that the zero set, zp, bisects each si volume-wise. And what do we mean by that? It means that for all I, like for S1, I'm looking at the part of Si where the polynomial is positive, and I'm looking at the part of Si where the polynomial is negative. Those will have the same volume. So for every Si, the part of Si where the polynomial is positive will be the same in volume as the part of Si where the polynomial is negative. That is what bisection means. So literally in half for all these. And now we weren't interested in bisecting sets of finite volume, positive volume. We're interested in bisecting sets of points. So that is the third step. Oh, I didn't prove this. I should have proved this. So let's just prove this here. This bisection lemma. I'm looking for a polynomial that does this. Zero set should do the splitting, right? So I'm looking for a degree and a non-zero polynomial in n variables of at most this degree that does this splitting in equal parts. In other words, such that the part of S1 where the polynomial is positive has same volume as the part of S1 where the polynomial is negative. And so on, up to the final set. Its part where the polynomial is positive should have the same size as this part where the polynomial is negative. Okay. This means that I want to find the polynomial such that all these differences are zero. And therefore, this m tuple is the zero vector inside Rm. That's what I want. I want to show that there is a polynomial that is mapped to, if I map every polynomial to this m tuple, I want to show that one of them goes to zero. And what I'll do is I'll map a sphere of polynomials to these m tuples and find one that goes to zero via the Coulomb theorem. So what I'll do, what do I mean by sphere of polynomials? So the polynomial has a degree at most d, right? Here. I will identify it with its vector of coefficients. So we'll identify it with its vector of how many coefficients? There are d plus n choose n coefficients. And the length of a polynomial would just be the length of this vector, the Euclidean length of this vector. Square root of sum of squares of coordinates. So what I'll do is I'll define a map from the sphere of the space of polynomials of degree at most d into Rm that will take any polynomial to this m tuple that I had right here. And this map is continuous because if I change the coefficients of a polynomial by very little, then the areas where the polynomial is positive or negative won't change too much. And it's also odd because if you take minus p, then that becomes negative when p was positive and becomes positive when p was negative. So all these all these pairs are swapped and you get a minus sign when you apply the function to minus b. So by the Borsuk-Ulam theorem, there exists a polynomial non-zero because it should be in the sphere, right, in the unit sphere, and therefore it's non-zero, such that it's mapped to 0. Okay, and that's what I wanted. It bisects everything, as long as I can apply the theorem. As long as I can apply the Borsuk-Ulam theorem. So there was a little caveat here that I had the map from the sphere into the hyperplane below. That was important. So Rm should live inside this hyperplane that's below the sphere, should be inside it. And all I need is that m is at most d plus n to n minus 1. For every d satisfying this, we are okay. We can find the polynomial of at most degree d bisecting. That's equivalent to saying that m is at most d to the n, pretty much, or that d is at least m to the 1 over n. For every d, in other words, beyond this threshold, that's about m to the 1 over n, for any d beyond that, no matter which you choose, you can find the polynomial of at most that degree doing the bisection you want. And you'll just work with the lowest d possible. So we'll work with d about m to the 1 over n. This means that even for that d, as low as possible, I can still apply the Borsuk-Ulam theorem, and I can find the polynomial of degree at most d, and therefore at most number of sets to the 1 over n, performing the bisection. Okay, so I like this, I wanted to show it. And now we upgrade the bisection lemma for sets of positive volume to a discrete bisection lemma for sets that are finite sets of points. So instead of a set of positive volume here, I have a finite set of points. Similarly here, here, and so on. It says the same thing pretty much, that if you have m sets, finite sets of points, you can find a non-zero polynomial of degree at most the number of sets to the 1 over n, bisecting each of these. And now we need to be careful about what bisection means. It means that for every set, so say this one, you look again at the part where the polynomial is positive and the part where the polynomial is negative. And in each of the two, you have at most half the points of Si. So the size of S, the number of points in Si, where the polynomial is positive, is at most half the points of Si. And the number of points in Si where the polynomial is negative is again at most half the points of Si. The point is, this is what you get if you try to upgrade the previous continuous bisection to discrete bisection, because the way you do it is you just thicken your points just slightly so that they become little balls, and suddenly your sets are sets of finite and positive volume, and you can bisect all of them with a polynomial. And then you just start reducing the radius, and you do a limiting argument, where eventually this is the kind of discrete bisection you get. I just wanted to say here what this bisection means even for S2. So notice S2 has 5 points here. If the zero set passed through the 3 at the bottom, like this, it would still be bisecting S2, because on the one side, on the one side, okay, no panic. On the one side where the polynomial is positive, I get 2 points, that's at most half. And the other side where the polynomial is negative, I get 0 points, which is again at most half. So bisection can be a little counterintuitive sometimes for discrete sets. In any case, we're done almost. Now we'll do this iteration we described earlier. we have a finite set of points. We want to show that we can use a low degree polynomial, at most this degree, to chop it up in a specific number of parts that depends on this degree. And each part should contain at most the average number of points. Let's see how to do that. We just iterate the discrete bisection lemma. So let me write the goal, by the way. The goal is this is polynomial partitioning, that's what it says. There is a polynomial of at most this degree, whose zero set will split in this number of cells, each containing at most the average points. So once you choose a degree, the number of cells, as we said, that you're aiming for is prescribed. So that's fixed. What we'll do is we'll bisect this set. We'll bisect it once, we'll bisect it again, until we get to the number of cells we want. That's the plan. So here is the first stage. You just had one set, and you want to split it into. You can do it with a plane, that part. So you just need a polynomial of very low degree, at most the number of sets, as we said, it's just 1, to the 1 over n, bisecting S. So on the part where P1 is positive, we have at most half the points, that's the first cell here. And on the part where P1 is negative, we again have at most half the points. So we have two cells, each with at most half the points. So each with at most the average number of points. And you start seeing what cell means. Two cells, each is fully determined by a sign for this polynomial, either positive or negative. And now we have two cells from this first step. We will bisect both simultaneously with a zero set of a very low degree polynomial. What degree? Will be at most the number of sets, that's 2 to the 1 over n. So that's what I'm writing here. There exists a polynomial P2 of very low degree, at most 2 to the 1 over n, number of previous cells to the 1 over n, that bisects both the cells. So here was the original cell on the right, where the polynomial P1 was negative. We have split in two parts, one where the polynomial P2 is positive and one where P2 is negative. And similarly, this cell was split in two parts, one where P2 is positive and one where P2 is negative. So the two cells have become 4, have doubled, and each still contains at most the average number of points. And again, the cells are determined fully by the signs of the two polynomials we have so far used. And the zero set I have drawn in this picture, so I have drawn these two zero sets. That's the zero set of the product of P1 and P2. And its degree is very small. It's at most the sum of these two degrees. So that's a polynomial, the product, that achieves this splitting in 4 cells. And you keep going until you finish, like until you get to the cells you want. So just let me write one more. The third step, you'll bisect all of these 4 cells with a zero set of degree at most, number of previous cells to the 1 over n, and you'll get 8 cells, 2 to the 3, each containing at most the average number of points. And you keep going. Final, let's say, step, you have 2 to the k minus 1 cells from before. So you use a degree at most, that number of cells to the 1 over n, to bisect everything once more. So you get 2 to the k cells, each with at most the average points. And you stop when this 2 to the k is exactly what you wanted. It's d to the n. That's the cells you wanted to have for the d you chose at the beginning. And you see that you have essentially split your picture in at most equal parts with these red zero sets simultaneously. So these red zero sets, together united, are the zero set of the product of all these polynomials. So the zero set I'm using has degree at most the sum of the degrees that I used all the way. And you see that is the geometric progression. So with the ratio 2 to the 1 over n. So you know pretty much how much it is equal to. So if the cells are 2 to the k, then the degree used for the final, like for the whole picture to be created, is the number of cells to the 1 over n, pretty much. So if the cells are d to the n, then the degree used is about d, and you just stop, like you have to be careful with the constant, multiplicative constant, the point where you stop, so that the degree is at most, clearly, literally at most d, and not with a wiggle. That's all. So that is the idea of how you prove polynomial partitioning. And on Thursday, we'll do 2 refined versions of the joints problem to apply it and see how we deal with the cellular case, at least. That's standardized. So that's it. I guess we could stop the recording now and we could have questions.